Well, a warm welcome indeed. Thank you for being here. Get yourself ready with a notebook. Grab a pencil or a pen if you're so bold. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have a most interesting problem involving a system of linear equations. Here's the system. You'll notice that there's a very obvious k value that is a missing value. And the goal is this. Find the value for k such that this system of linear equations has infinitely many solutions. In other words, an infinite number of solutions. And this is going to motivate exactly how we approach this problem. The fact that this solution set is infinite means something very particular about these two equations. So I'll give you a few minutes to figure out what the value of k should be if you want to attempt this on your own. You can pause the video, give it a go. What I also want you to do is I want you to graph both of these equations and describe their relationship. I guess I'll spoil it and say the relationship of the lines. I wanted to leave that out, but it should be obvious that these are lines. If it's not obvious that these are lines, what are we doing here? Okay, so as I said, give yourself some time to try that out. Then you can unpause the video and see how we did it here. Now, because this problem says that the system will have infinitely many solutions, what that means is that these two equations are the same equation multiplied by some constant value. But they can be reduced or simplified to the exact same equation. That's what it means for these to have infinitely many solutions, because if they are indeed the same equation, they would have any x and y values in common. Every x and y value that one of them has, the other will have, if they're the same equation. So therefore, if these two equations are essentially the same, then the system will have infinitely many solutions. Well, these equations do not look the same right off the bat. This one has 2/3 x minus 1/4 of y. That's very different from this minus 1/3 of y. Then it has equals to 6, which is also quite different from this equals to 8. So how can we turn one of the equations into the other equation? Or another way to think about this is how can we turn them both into the same equation? Sometimes it's easier to think about that. So here we go. We want to try to turn the 6 into an 8. What we don't want to do is we don't want to add 2 on both sides. Even though that's a valid step and it's true, we don't necessarily want to do that. You could do that. In fact, I'll probably show you how that could still work out after I do what my preferred solution would be. What we'd rather do is see how can I multiply this equation to turn it into this one. Right, so we could multiply the equation by 8/6 on both sides. And if we do that, we guarantee that the right side is going to be equals to 8. Right? So that's one way to go about it. 8/6 is the same as 4/3. So if you wanted to multiply both sides by 4/3, that's also equivalent. I just wanted to make it very obvious that this would turn into an 8. Okay, now what should we do though? That's still not my preferred method. My preferred method in this case is to identify the least common multiple of the 6 and the 8. That way I know that I can multiply each equation by some number, maybe not the same number, but I can multiply each equation by a number and result in the same common multiple. So I'm going to take equation number 1 and take equation number 2, and I'm going to do this. Their least common multiple between 6 and 8 is 24. So if I multiply the equation 1 by 4, then what I'm going to end up with is 8/3 of x minus, oh, that's kind of nice to multiply this by 4 because 1/4 times 4 is just 1. So minus y equals 24. Meanwhile, I should multiply the second equation by 3 because that will turn the 8 into a 24. So what am I going to have? I'm going to have 3k times x minus, look at that, 1/3 times 3 is just 1, so I have minus y, that matches, equals 24. And if we think about it, it should match, right? Because we know that this is going to have infinitely many solutions. The equations, like I said earlier, should essentially be the same, or they can be turned into the same quite easily. So now that these are the same equation, I can match up the 8/3 with the 3k. So 8/3 equals 3k. And if I divide both sides by 3, I get 8/9 equals k. And that is our value for k. That is going to make this system have infinitely many solutions. Okay, now let's try to graph these two lines. And I think it might be easiest to graph if we get everything in what we call y equals mx plus b form. So let's take 2/3 of x. It's actually easiest to graph from this form. You know what? I'm changing my mind. I'm going to use this format. The reason why it's easiest to graph in this format is because we can use the intercepts very easily. What is the x-intercept going to be? What is the y-intercept going to be? Well, the x-intercept is when y equals to 0. So we just cover this up, right? And we solve, and we say that 2/3 of x equals 6. So 2x equals 18, and x equals 9. Now what about the y-intercept? Pretty much do the same thing, just make the x equals to 0. And now we have negative 1/4 y equals 6, multiply both sides by negative 4. And we get y equals negative 24. So the y-intercept is 0, negative 24. This is easy enough to graph. You can sketch it. You don't have to do a perfect graph, but if you want to use Desmos or something and get a really nice graph, you're free to do that. 9, 0 might be somewhere here, and 0, negative 24 might be somewhere here. So here's the line. Bam. Now, let's take a look at the second equation. I forgot to label this. Equation 1. Let's take a look at the second equation, equation 2, which was kx. We found out that that was 8/9 x minus 1/3 of y equals to 8. Okay. Well, let's do the same thing. Let's find out what is our x-intercept. Let's find out what is our y-intercept. Pretty easy to find the x-intercept. You just make y equals 0. And we get 8/9 x equals 8. So that means 1/9 x equals 1. So x equals 9. Ah, interesting. Same x-intercept. All right, you ready for the surprise, right? You kind of know what's coming, right? The y-intercept would make x equal to 0, so we block that off. And we get negative 1/3 y equals 8, which means y equals, you guessed it, negative 24. So what is the relationship of these two lines? And if you try to graph these both on Desmos, you'll notice there's only one line. They're the same line. this is a description or an illustration of how they have infinitely many solutions, because these lines overlap. So every single point on each line is shared, and any point which is shared between these two lines is considered to represent a solution to the system of equations. Now, I mentioned there are other ways to solve these systems, and there definitely are. One approach, which is pretty smart if you can see it, is to notice that these are just fractions of y. So that also could motivate you to multiply this one by 4 and to multiply this one by 3. That is possible. We're going to take a look at the sort of unique method of adding 2 on both sides. So what happens there? What happens when we get 2/3 x minus 1/4 y plus 2 equals 8? Then we can set it equal to kx minus 1/3 y. But what you'll notice happens if we do this is now we have one equation with 2 variables. And the problem here is that we cannot just cancel some variables on both sides. We do not have an even amount to cancel on both sides. So this method would not get us anywhere. It would be much more complicated than that. Let's see, the other method that I talked about, which will actually work, is if we were to multiply both sides of the equation by 8/6, and we wouldn't have to do anything to the second equation. So we'd be multiplying this side by 8/6, multiplying this side by 8/6. So I would have, let's see, cancel this 2 with a 3. So that gives us 8/9. X, 8/6 times -1/4, you cancel that, get a 1 and a 2, this is still a 6. Cancel that, get 1 and a 3. So we'd have minus 1/3 y equals 8. And there you have it. It's basically the exact same equation as equation 2, except it has a coefficient for the x. So that tells us right off the bat that k equals 8/9. So you might notice that was actually faster than the solution method that I went with. I think the method that I went with is pretty safe. It avoids fractions, with students, they tend to prefer that when you avoid fractions, but honestly, you guys gotta grow up. If you're trying to avoid fractions every step of the way, you should probably just get better at fractions. If you have a simpler method that doesn't require fractions, then by all means, do the simpler method, but don't just avoid fractions because they're scary. All right, I think that's enough blab out of me. I hope you got something out of this problem and reminded yourself that if a system of linear equations has infinitely many solutions, then those graphs represent the same line. And that means that the equations are essentially the same. They might just differ by being multiplied by some constant. Okay, that's enough blab out of me. I'll see you guys next time.